Okay, so for this exam, we are going to be looking over fractions and fraction models and just different ways to kind of visualize fractions really and to make them seem not so scary. Okay, let's go. Okay, so our first problem, we are looking at pattern blocks, and we are doing this to kind of manipulate fractions and to see them visually and kind of really what fractions are in a way. And in this one, we have a hexagon, a rhombus, a triangle, and a trapezoid. And what we're going to do is we're going to spend time stacking them on top of each other and manipulating them to see how many times one will go into the other. So for the first one we're going to use the hexagon as the base, and we're going to put the trapezoid on top of it. Right here we can see I put the trapezoid on there once, twice. So it took 2 times to fill up the hexagon, so we can say that the trapezoid was 1 out of 2 for the hexagon. Next I did the triangle. Added 1 triangle, 2, 3, 4, 5, 6. So the triangle is 1 out of 6, so 1/6. The rhombus is 1/3 because it takes 3 of them to fill up the base of the hexagon. Next I use a trapezoid as the base. For the hexagon, you can see that it completely covered it, but we know from the last problem that it took 2 of the trapezoids to cover the hexagon, so we can say the hexagon doubles the trapezoid, so it makes it 2/1. Next we'll use the triangle. We will put that on top of the trapezoid, and we can see that we've got 1, 2, and there's room for 1 more right there, so that'd be 3. So it's 1/3 of the trapezoid. The rhombus does not quite fit into the trapezoid perfectly, but we can see that there'd be room for 1 of the triangles, and then we can look right over at the other and see that the triangles take up 1/3, so the rhombus equals 2/3 of the trapezoid. Next, I use a triangle as the base. I put the hexagon behind the triangle, and so the hexagon equals 6/1 triangles, 6/1. Next, I did the trapezoid, put that behind it, and that equals 3/1. Next, I did the rhombus, and the triangle is 1/2 of the rhombus, so that's 2/1 triangles. Lastly, I did the rhombus base. Hexagon underneath the rhombus again, we've got 3/1. Trapezoid, we've got 3/2. And triangle, we've got 1/2. For problem 2, we are looking at a man who bought a rope and we are trying to decide how long the rope was. So he was using the rope for a bow painter in the front of his canoe, and then he used the rest to tie up a roll of carpet. We want to figure out exactly how much rope he had if he had 36 feet of rope left over when he was done using the rope. So we're going to do this by using a number line. So here I have our rope, or just a line. We're going to pretend it's a rope. And so I have equals 36 feet, but that is not the whole rope. That is just the remainder of the rope. So we have cut off 1/3 of the rope for what he used for his canoe. So we're going to pretend that this side right here no longer exists. For now, it's just not there. Next, he used 1/4 of the remaining rope to roll up some carpet. So now everything to the left of this orange line doesn't exist. It's not there. So we're just going to look over here for right now. So this right here equals 36 feet. And to be able to find the total, we're going to want to break this up into even pieces. I decided to break it up into 2 pieces. So now, how many, 36 divided by 2 equals what? 18. So each of these pieces is 18 feet. Well, we can see now, we're going to look at the rope as a whole again, and we're going to just go ahead and ignore the 1/3 and the 1/4, and we're going to go ahead and break it up again evenly. So to do that, break it up into 4 pieces, and they're all equal to 18 feet. So we multiply 4 times 18, and we get the length of the whole rope is 72 feet. For problem 3, we're representing these addition and subtraction problems using a number line and fraction strips. So it's just visualizing again. There's our number line and our fraction strips. Number line, fraction strips. It just repeats. Problem 4, we are using shading to kind of these circles to figure out the fraction and how they work. So we've got 3 times, or multiplying fractions, excuse me. So we've got 3 times 1/4. So this whole circle is 4. So out of these, we're shading 1/4 3 times. So I put an X. There's 1 1/4. Another X. There's 2 1/4. Another X. There's 3 1/4. So we can count it together. We got 1, 2, 3 out of 4. Same concept over here, but since we ran out of circles, I just added another one. So let's count. We go 1, 2, 3, 4, 5, 6. So that's 6/4. This one is 5 5/8. So I have created these circles of 5/8 of 8s with 5 shaded in. So let's count how many are shaded total. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So that 25/8. The next problem is the exact same, but because we know our multiplication rules and we know that when we multiply a positive number by a negative number, the number is negative. So this would be the same answer as the previous problem, just negative. So this is a tanagram. Excuse me if I say it wrong. But for this is more of a visual thing. We're kind of just looking at what we did the first problem, but we're not going to stack them on top of each other. This is what I did was I saw A and B are the most obvious ones, and they take up, as a whole, together, they take up half. So if you cut them in half again, that makes it a 1/4. So I was looking, and I've noticed that G took up a half of B if I placed it in the corner of B. So I knew that that must be, if that was a half of a quarter, that had to be an 1/8. So it's like, okay, so I was looking and I saw that C was half of G. So half of an 1/8 is a 16th. And I saw that E was the exact same as C, so that must be a 16th as well. I also noticed that C and E will combine together to make D as well as F. So I know that these two have to both be 1/8 as well. And problem 6 is closest to the real life world we will get when it comes to fractions. For this, someone wants to make 12 brownies, but they only have a recipe that makes 16. So what we're going to have to do is we're going to have to set up an equation. The equation is desired serving size over recipe serving size multiplied by the ingredient that is called for. So we're going to have 12/16, which can be simplified, and so it can be more simple for us. We are going to go ahead and simplify that to 3/4. And then we're going to multiply these by the number of the recipe that each calls for, which I have done that right down here. I, however, did not change the amount of eggs that are here because you cannot really put a fraction of an egg into a recipe. And since we are not going for less than half or half of the recipe, I didn't take an egg out because we have more than 8. So I feel like it'd be better to add a little bit more than to not have quite enough of the egg. And that is it. Thanks for listening to fractions with me.